Good afternoon. This is Scott Sanford of the University of Wisconsin. Be the moderator today for the today's Refueling Wisconsin with Wood Energy series. This is brought to you by a group of interested parties. We've got the University of Wisconsin, University of Wisconsin Extension, the State Energy Office, the U.S. Forest Service, which provided most of the support for this. Wisconsin DNR, along with others. So today we're going to talk about wood energy systems on the commercial and industrial side. And with us today we have Lou McCurry, who's with the U.S. Forest Service. He's a bioenergy or bioproducts coordinator, and Tom Wilson from Wilson Engineering Services. So they're going to take you through industrial size equipment. So I think we're going to start with Lou. You there, Lou?
Is he muted?
Yeah, he disappeared. We lost Lou. All right.
Can you hear me?
Yep.
Yes.
You kind of disappeared there for a minute. Okay.
Oh, I'm sorry. Again, thank you for joining the webinar, folks. And the Forest Service is nationally very interested in the use of woody biomass, wood energy to address sustainable energy needs of the country, and also to provide markets that will help us and all forest managers address issues related to forest health and climate change. We really want to utilize wood energy to try to address the high energy costs in different parts of the country, as well as developing a long-term sustainable energy solution that will allow the use of wood to address serious climate change issues. So we are supportive through our work with state wood energy teams across the country to help folks better understand the use of wood energy, also how to put in projects that are very efficient so that we will conserve and use efficiently the wood resource that is utilized for energy across the country. In the northeastern area, that area from Minnesota to Missouri, Maryland to Maine, we are delivering our program through our wood energy technical assistance team, which is designed to try to help facility owners evaluate and implement wood energy projects. And we believe that we do it in a way that is both technology and vendor neutral. The partners in our wood energy technical assistance team is our USDA Forest Service Wood Education and Resource Center that's located in Princeton, West Virginia. And we work cooperatively with Wilson Engineering Services that's located in Meadville, Pennsylvania, to do this work across our northeastern area and also in collaboration with our southern region that's based in Atlanta. When we first visit with a facility owner, basically we really have a mission to identify their perspectives and what they hope to get out of the use of wind energy. Sometimes we run into, I'd like to generate all the electricity that I use from biomass, and that may be a little too aggressive, and we need to work with that owner to help them better understand how they can use wood energy in their particular business. When we take a look at a project, really the potential budget for that project is dependent on the energy, how much money is currently being spent on energy, what the difference between that energy spend and a wood energy option would be, and then from the owner's perspective, what sort of cash flow are they willing to need for their business decision? Do they need this system to pay off in the first year, or can they have a couple of years of negative cash flow before the system starts paying itself off? So that's a couple of the questions that we need to really sit down with them and understand their expectations for their system. When we sit down with the owner, then there's a certain set of basic data, basic system data that we need for analyzing the project and the opportunity that they are going to have. Of course, annual fuel use and its cost is very, very important. The more detailed information we can have on this annual fuel use, if we can have it on a monthly basis, that's really kind of the best information that we can have. And if we can have 2 or 3 years of that data, it enhances the ability of our analysis to give them a really good understanding of how wood energy is going to fit at their business. We always ask for electricity costs. Depending on what these costs are, the opportunity to use combined heat and power project at their site is maybe an option, and in many cases that may be able to, by generating some of that some power at their site, we may be able to influence their overall electricity rates as well. The next thing we need to know is how they generate heat, what the distribution of that heat will be, and you know, is it a central heating system that's run from one boiler room, or are there multiple boiler rooms around the facility, and just how that heat is used. Is it simply for space heating, or is it for process heating, or a combination thereof? The better we understand how their system operates, the more detailed our analysis can be. And then we take that data and do some thermal load modeling to better understand how that system works over the course of the year. So when we get that fossil fuel use and its cost is key to the analysis of the project and the financial benefits that can accrue from wood energy, we're going to establish that the fossil fuel baseline from existing records, hopefully. If their records aren't in place, then we're going to have to do some modeling based on their building type and where it's located and weather data. We also want to take a look if there's been increases in fuel use or decreases in fuel use, what has caused those, whether it's weather, or if they've done efficiency projects, or they've changed their processes. All of those different factors come into the analysis of the use model. Once we've established that baseline fuel use and cost and done some projections, then we'd go back to the owner and make sure that we've captured both their baseline usage and cost, and that they agree with the basic analysis of their fuel use over that period of time that we've analyzed. You know, energy can be used in a lot of different ways. Heat energy, thermal energy in a system. We can, you know, the existing system may be a steam system, and that steam is developed at different pressures, different temperatures. Can be used for heating, humidification, process energy. We need to know what the operating schedule is and just what the range of pressures and temperatures that are required in the system, so that we can determine how we can meet those same requirements using wood. If it's a hot water system, what temperatures are needed at different parts of the building, different uses, whether it's simply heating a pool or providing domestic hot water heating, drying at a laundry. All those things come into play. What the building or process operating schedule is, when do you need the highest temperature water? Are there different zones that are going to need different temperatures at different times of the day? And what the restrictions are as far as plus or minus 5 or 10 degrees to those requirements. Finally, forced hot air systems. We can use existing forced hot air furnaces and build in heat exchangers, but we need to know the temperatures that are required, what the airflow in those systems needs to be, again, what processes they may be serving, what parts of the building, and what kind of variability there are in those demands across the day and across the year. So we use that data and model the loads. Here's a hourly steam demand at the Veterans Medical Center, Veterans Affairs Medical Center in Chillicothe, Ohio. And as you can see from the left part of the graph to the right part of the graph on the x-axis, it goes from October to September, so that the highest heat demands, of course, as you'd expect, are in mid-January. Once we've got that, we can look at a load duration curve, which helps you better understand when the highest demand is and what portion of your overall heat load is in that highest demand area. Here, this graph is for Gunderson Lutheran Hospital in La Crosse, Wisconsin, southwest Wisconsin, and you can see that they have a pretty stable heat demand for most of the year, and that allows us to do some things, and that allowed them to do some things with combined heat and power. This gives you an idea, based on the load curves and our understanding the system, that we could cover most of the load with one boiler, but with 2 boilers, working in tandem, we could cover all the load at this site, and that enables us to eliminate the use of fossil fuels if that's what an owner would like to do. One of the biggest issues is trying to add load. The more load that we can get on the wood energy system, the better. That's just going to build into increased fuel savings. So if there's adjacent buildings that are available, adjacent owners that are interested in participating in the project, any of those kinds of opportunities we want to try to address with the owner, so that we can build more load and increase the opportunity to share operating costs, and also decrease investment costs by any one owner. Again, as part of the potential project trying to address additional loads, there is the opportunity, if the load is of appropriate size and capacity across the year, to add thermally led combined heat and power, and that'll add load during different parts of the year, and it also will have a positive impact in most cases on project economics. In most cases, with thermally led CHP, we're talking about electricity costs for that generated from the CHP unit in the 2 to 3 cent per kilowatt hour range versus utility costs, electric costs that may range from 6 cents a kilowatt hour to 18 to 20 cents per kilowatt hour, depending on what part of the country you're in. Another opportunity to add load is air conditioning and chilling, and that may help you run your boiler year-round and provide that kind of load in the summertime, which also can help balance a load for combined heat and power project. And it may also help you reduce your electrical demand and reduce your peak electric demand during the summertime. So we're going to take a break here, and if there's any questions on our technical assistance program or what you've seen so
Crap. Whoop. All right. If anybody has any questions, you can either type them in the chat box, or if you raise your hand, which is one of the icons, or actually there's only a few of us here, so I'm going to unmute everybody's mic. So if you have a question, just go ahead and say it.
sounds like everything was understandable, Scott.
Yep. So I guess we move on.
We move on to Tom.
Good afternoon. My name is Tom Wilson, Wilson Engineering Services, and we've been working with Lou on providing technical assistance for about 5 years now. And we've looked at well over 100 projects. We've done feasibility studies on the range of 90 projects. And somewhere at around 40% of those projects have been implemented. And I think it's a kind of a tribute to the Forest Service, this model that they were willing to kind of experiment a little bit on. You know, I think what's happened in the past and what happens sometimes is that, you know, there's a preliminary feasibility study, and the challenge is to give the owner enough information and confidence to make a decision. And often that is lacking without some detailed engineering pieces to the puzzle. And I think that's probably what has made Lou's program so successful, is that he's had the flexibility to provide additional services or more detailed services that can help the owner make a financial decision. And you know, I think that's a pretty good record if you can implement 40% of the projects that you actually end up doing a feasibility study on. So I'm going to talk a little bit about the energy system design and operating considerations, just kind of what the issues are and what you have to address on these projects and things you need to take into account when you're trying to figure out, you know, what the overall project is going to cost and what the economics are going to be on the backside for the owner. So the first thing, and I think the most important thing, is that we want these systems to be able to be an opportunity fuel user, and you know, minimal processing, if that's what's available on these larger systems, chip and institutional and industrial size chip systems. You need to build in the flexibility in fuel handling and fuel systems that you can use multiple different types of fuel. Now, every boiler operator will tell you that the fuel makes the difference and the perfect chip is the ideal chip, and that's what you want to buy. But the truth is that if you use those economics, a lot of these projects wouldn't and couldn't happen. So you need to be flexible about the fuel that's available now and the fuel that would be available in the future, and you need to design systems that can take advantage of that. And then, you know, boiler room equipment is another consideration, exactly what types of systems you want or what kind of pieces you need in the system. You need to look at the facility and building served, and you need to talk to the owner about staffing. You know, some of these institutional places now, they've got a heating system where it's just there and you ignore it. We have other places who have full maintenance staffs, and they're very comfortable providing additional services like raking ash or you know, handling with more oversized pieces, or just being more hands-on. So a real consideration of the design of the system is what exactly does the owner expect, what's acceptable to the owner. These systems, the first thing that happens, you get people out to look at them, and they are always surprised. They're not what they expect. They're efficient, they're clean burning, and they're very automated. Lots of PLC controls control the burning process and the fuel delivery process. If you think about this, it's really a logistics problem with materials handling. It's wood chips and getting them reclaimed and delivered, and ash, getting rid of it and getting it out. So, these solid fuel systems are really a materials handling problem to solve. So the system and the cost of the system really is based on fuel type. And typically the way we like to divide these up are, if you look at cordwood systems, they're small systems, usually minimal investment. They're more labor intensive, but the opportunity is there. And usually the fuel is either produced on site, or they've got some relationship with the fuel provider in most cases where we put in these systems. It's a little bit cheaper than pellets, but it's always more expensive than to purchase. It's always more expensive than wood chips, and it's and simply because of the capital or the intensive labor that it's required to harvest and handle and move it. We try to design systems that minimizes the number of times you have to handle the cordwood. Wood chips have the highest capital cost, but they also provide us with the greatest opportunity for return. And pellets are very automated. They can be more automated than wood chips, actually. They usually almost always have the potential for self-starting, which gives them a little more flexibility and range of load that they can cover and sizing of systems. But they also have a lower fuel opportunity cost. Right now, pellets in the east, at least, and you compare that to propane, and there's not much fuel advantage or fuel cost savings. So, you're limited to going against fuel oil, and so it kind of limits the market when there's not a lot of savings with pellets. So, those are some of the challenges with trying to implement systems. Again, there's lots of appliances out there. There's a plug and play where you can just drop off. You see that green container or green storage container. Inside of that is a thermal storage unit, all the pumps and controls, and this Powe boiler, wood boiler. It's about a 500,000 BTU an hour system. You can see on the right they have distribution. In this case, where this is assembled, I think that's distribution to 3 facilities, buy and return, and there's an option for a 4th facility set up there. These 2 projects, this one is done at Harvard on the left, and the one on the right is down in Missouri, a small school in Missouri. And they're both a little bit automated in the way they handle pallets, the cordwood. The one on the left, they have students that come up and work in the summer, and they load these pallets with, I think it's about a ton of wood on a pallet, and they store them that way for drying, and then they deliver them with a forklift. They have a load cell on a little hand cart, forklift hand cart, that tells them the weight of the fuel. They measure the moisture content, and they do that for some research purposes at Harvard. And they minimize the handling, because once it's stacked in these, they can move a ton of time of wood, and it's delivered then directly into the boiler. The one on the right, they literally bought a cart. They can put about 2 tons of wood, cordwood, a little over a cord on this cart. They back it into the building where they fill the cordwood boilers, and they only handle it once. Once it's thrown on the cart, it's backed in there, unloaded directly from the cart into the boilers. Containerized pellet systems, whether it's cordwood or pellet systems, they really minimize the development costs. You kind of cut the engineer out of the equation. You make it so that the soft cost, or not the soft cost, but the development cost of a project are minimal. And also, you cut down a lot on the time. So the pellet system you look at here is in a shipping container. It's just dropped off on a pad. you plug in the water supply and return, you supply potable water into the system, back up, you pipe your pellets into the boiler, and it's all self-contained in one unit. A lot more flexibility with pellets on delivery. You can use flexible augers, so you can put in many different combinations and locations in order to get the pellets from the fuel storage to the boiler room. On the left is an installation we did in the basement of an old church up in New Hampshire. On the right, it's an outdoor pellet grain bin. That grain bin is probably in the range of $4,000 to $5,000 for the bin. Whole fuel delivery and storage system is probably well less than $10,000. Pneumatically, they can blow them a long way. This is in New England. New England is probably a lot further advanced than the other areas of the country as far as bulk fuel delivery. We have had systems or places that use auger trucks, feed the auger trucks to deliver the pellets. They work just fine. It's just you got to be right next to the fuel bin. Here's two wood chip boilers. The one on the right is about a 100 horsepower boiler, and the one on the left is a 500 horsepower boiler. So you can see that they come in various sizes. There's probably not too much. We've done down to 50 horsepower for wood chip systems, but that's kind of on the low end. Typically 100 horsepower is about the minimum size, just because of the other economics and the amount of load you need to justify the capital investment for handling bulk chips. Key design points are maximizing cash flow is usually what the goal is in the end. It's some form or some way to do that. You got to balance the savings with the investment. So fuel availability and price, the level of automation that the owner requires or expects, and what's the savings opportunity. And once you identify those numbers, it kind of narrows down the direction you're going to go in with the project. There's lots of times there's lots of loads that could be used, and they're using lots of fossil fuels, but what loads are really practical to connect? The cost of connecting rooftop systems sometimes are very prohibitive to try to pick up the loads and not practical. And there could be an adjacent building, but that adjacent building is 500 yards away and has a minimal load, and it may not be practical to go after that load. Another consideration is, can you add CHP or an absorption chiller to make this system work? I'll give you a quick example of a project where the absorption chiller made a ton of sense, because what it let us do was run the boiler system to pick up an existing heat load. This was a VA hospital. They had a summertime heat load. We installed a 600 horsepower boiler that picked up about 90% of the load in the winter months. But they had about 15 to 20% of the winter load, or the size of the boiler, in the summertime, and it was a lot of, for 5 months, there was a lot of fuel usage, fossil fuel usage, that you couldn't pick up if you would have not found an additional load. And so in this case, they were building a new building. We were able to put an absorption chiller in that building, a 250-ton absorption chiller. What it did was allow that biomass unit to pick up that additional heat load, that 100 horsepower of heat load that was there in the summer, and added another 150 horsepower of chilling load, peak chilling load, that allow us to run year-round, and made the project more profitable for the owner. And I can't stress this enough. Two items on here: thermal storage and fuel flexibility. Thermal storage, if you get down and try to pencil everything out, it's hard to capture what happens here, but biomass systems, especially wood chip systems, are not as responsive as fossil fuel systems, not nearly as responsive. And once you've got all this thermal mass there inside that boiler or inside that firebox, you can't shut it down as easily as you could a conventional system where you're just injecting fuel into the system. So that thermal storage is really critical to making this thing be responsive to the owner. It's really responsive to the load. It's also very critical to minimizing emissions, because you can tune this boiler so that it ramps up a little bit slower, allowing the thermal storage to take over. You spend a lot less time varying firing rates of that boiler, And as you change firing rates or you go from low firing to higher firing, there's a lot of emissions that take place. Also in the idle mode, there's a lot of emissions that take place. And what thermal storage does, it really helps both the overall efficiency of the system, responsiveness of the system, and greatly reduces emissions of the system during those times of changing loads. And fuel flexibility. By all means, there's 1,000 ways to do it, but put in handling systems that can handle multiple fuels, can take care of oversized pieces, get them out of the system, and allow the owner to have more options when it comes to buying the fuel. The final item to consider is emission controls. The new boiler MACT rules, area source rules for units that are under 10 million BTUs an hour of input require different kind of control systems for units than units that are over 10 million, and they can make substantial differences to the cost of a project. The cost of an ESP, which is our preferred control method in institutional type settings because of the amount of labor and the work versus a baghouse. For a 300 horsepower boiler, it can add $250,000, $200,000 to the cost of a project. So emission controls are an important consideration when you're sizing and deciding on exactly what you're trying to accomplish with the system. The chip system, again, this is just a material handling issue, but you've got to worry about fuel storage, fuel delivery to the boiler, getting it to the combustion unit, and how you're going to get it into the combustion unit. Thermal storage is another component of the chip system, and then heat delivery. What are we doing on the other end, the backside? Every project we've ever done, the owner says, oh, I would like a month's worth of storage. I think that's where it probably starts, and practically that's just not going to happen because he can't afford that live bottom floor that's that kind of storage. And our advice to folks are that, look for 3 to 5 days of storage when peak demand hits and you're in the right ballpark. Make delivery of the fuel not your problem. Make it the problem of the person supplying your fuel. Almost all the systems we put in, and certainly in institutional cases where we're required to have meet some codes, we almost always have 100% redundancy in either a fossil fuel system or the existing system was in there, or we put in a new backup system that complements what we put in. And so it's not a disaster if you run out for a day or a half a day. You're not going to spend that much more money in the total year's fuel use versus spending another $500,000 on fuel storage. So, it seems like it's a sticking point in every project, but the bottom line is that, it's more than 3 to 5 days in the system is really a luxury and probably not needed and probably doesn't make any economic sense. You also have to design these systems so they'll take full truckloads. That's really the key. You want to be sure that you can have some fuel in storage to still operate and still be able to deliver a full truckload. And the full truckload varies by region of the country. In some places in the east, that's 30 tons, 32 tons. Some places in the east, that's 22 to 24 tons. But our goal is to usually design storage that can take full loads, 30-ton truckloads, and still have adequate supply there to run, and so that they don't have to wait till they empty the bin to take the next load. Several different ways, and we'll show some pictures here on how you can get fuel out of storage. There's traveling augers, there's hydraulic brakes. You can do at-grade systems. They work just fine. There's the spring and auger system. The spring and auger system, the one thing you have to be certain of that you pre-screen the fuel because it does not accommodate oversized pieces. So how are you going to separate out oversized pieces? We've seen some fairly simple, ingenious setups. Pinch point works. There's the traditional shaker table or rotary drum that will separate out oversized pieces. Pinch point can be any place that the fuel transitions or drops or changes direction. What tends to happen is longer pieces tend to align with the direction of travel on the belt just from the general physics of trying to move things along the belt. It bounces around and it will kind of align, and the long axis of the fuel will align with the direction of travel, so it allows you the opportunity to be very effective in separating pieces out with a pinch point. Delivery to the boiler, we've seen shaker tables delivered to stoker augers. We've had augers delivered to stoker augers, belts, drag chains. Pneumatic is another way you deliver to the boiler. That's it's kind of a hybrid system, and generally it's a little bit less effective or efficient, and you have a little less control of the combustion zones when you pneumatically deliver the fuel. But it's not uncommon to see those systems out there, especially at sawmills. So on the upper right-hand corner, you can see there's a wedge floor system. Basically, we call them rakes. There's hydraulic cylinders that move a wedge floor, or a wedge that lays on the floor, pulls material forward, and then it slides back. It's tapered so it slides back underneath the material and then keeps moving it forward. On the left is a large wedge floor system or hydraulic rake system with leveling screws to take advantage of moving material from the front of the storage to the back of the storage. You got to remember that where you place stuff in storage, it generally stays there and it's taken from there. These live floor systems do not rearrange it in the storage system, they just empty it from the storage system. In the lower right, you can see an example of a vibrating screen with perforations that allow the right-sized chips to fall through and the oversized chips to keep traveling out the end. So here's an example of opportunities. This is whole tree chips, direct quotes in New Hampshire. This stuff was 45 bucks a ton. It's mixed hardwood and softwood whole tree chips. Now here was a Bole chip. This was $56 a ton, and it was a hardwood Bole chip at that price. And again, here was Hog Fuel at a little different location. This Hog Fuel was delivered at 25 bucks a ton. So while the boiler manufacturer would love to have the perfect Bole chip, the truth is that it's pretty hard to overcome 2.5 times fuel cost by taking different products. So the owner went with this product and was very effective for him. So one of the items, if you look here, we like to design in ways to keep the site clean, so not a lot of handwork. So you see here, there's a cantilevered delivery. You see the yellow curb guards there that kind of keep people from falling over the edge. You move those out of the way and you back the truck in, and you're 6 feet inside of the building when you do that, and that storage is cantilevered over top of storage that's below, so that when you empty that truck, you're utilizing or filling more or less to the middle of that whole storage, so you make use of 100% of that storage. So the flip side of that is when the truck empties and he pulls away, pulls outside, then closes the door, everything is contained and it's attractive and neat from the outside. So all those things are don't add a lot of cost to projects, but they are a lot more effective if you can incorporate them into projects. Seen really creative spaces with fuel storage. You can see where the boiler is in this picture because in the back you can see the smokestack. That's they're using the existing stack at a school in south central Pennsylvania. They used the same smokestack to put in the wood boiler, and in order to be able to use the existing boiler room, they built this triangular shaped or wedge shaped addition on, and the way they made use of that space was they used these leveling screws to move product from the doorway back into the fuel storage, and then it had a live bottom traveling auger on the floor. This was in upstate New York at an old monastery that was bought by the Church Communities Association, and they made use of an old coal tipple or coal storage underneath the parking lot, put in hydraulically operated lift gates, and basically they flip these lift gates up, dump the dump truck into these two storage areas, and make use of an old coal bin underneath the basement area of an old monastery. And this is looking up through from that same picture at the same monastery. See how they rebuilt and redid the beams and the walls, and then the storage is basically right below the parking lot. Crotched Mountain Rehab Center, this is one of the more creative spaces that they made use of for fuel storage. Those two doors, you can look at the space. It's about 30 feet deep by approximately, I guess about 30 feet wide, 30 by 30 more or less. And in order to get fuel to the back and make use of the space, the height that they had, they put these this track system or this bridge system up over top of the storage. The recovery system is about 6 to 7 feet below where those wheels of the truck sit, and they're able to go clear to the back of this fuel storage place or bin and dump, fill up the complete back of it and then pull the front of it. They actually, in this 30 by 30 space, they can take 5 30-ton truckloads, so it's a very effective use of the space. Again, that's the same facility, Crotched Mountain. This is a rake system. I think this is a Eastman system that was put in at grade. You're looking at the rakes are on grade, the same level as the parking lot out front, and it was put into a 30 by 30 room in front of a boiler room at a small high school in southern Maine. And so they made very effective use of that space, minimal construction costs at grade rakes, and very effective. This is a picture of the traveling auger. Messerschmitt uses this design. A couple other companies have copied that design. And that auger moves back and forth along the bin on that track and pulls material. In this case, there's 2 augers. They've set it up with 2 or 1 augers. You can see either. They draw the fuel from about an 18-foot length and depth of the bin back onto the traveling belt. Spring agitator, this type of storage, it's very cost-effective and very efficient. It's very reliable too, but the real challenge here is that you cannot deal with oversized pieces. It's about a 6-inch auger, 4 to 6-inch auger, running in the bottom, tied to a gearbox that spring and head mechanism is sitting in the center of that circle. And the real challenge here is that if you don't have pre-screened chips, you're going to have problems plugging the system or not being able to deliver to the system. Then there's the worst of both worlds. I call it the semi-automated fuel handling system. They literally dump in the basement or the edge of, not basement, but the edge of a hospital, and they run around all these pillars and then dump it into an automated fuel delivery system. And not sure a lot of thought went into this system. Inline screening systems, the most common and the simplest, I think, is the shaker table with the perforations to allow the right size material to fall through and be carried to the boiler, and the oversized pieces to continue on and out into a reclaiming bin. Here's an example of thermal storage. This is a 2,000-gallon tank, and you can see that you have the line coming out of the top and you have the one going into the bottom. And basically, I think we're looking at the side that is on the boiler. The boiler draws off the bottom of the tank and delivers to the top of the tank. And you know, there are some rules of thumb. There's lots of ways you can decide how to size thermal storage. But roughly, you're looking for about 15 minutes of the capacity of the system in a chip system in the thermal storage tank, or a rough rule of thumb is about 75 to 100 gallons for every 100,000 BTUs of capacity. One of the real problems we run into is people confuse thermal storage with thermal mass. Thermal storage is, by definition, that temperature that you store water at or store energy at that's above the planned delivery temperature. So if you wanted to distribute water at 170 and you were storing at 190, you would blend it, take some out of the tank, you would mix it with the return water from the system, a little mixing valve. The little mixing valve you see here is on a 100,000 BTU-hour boiler, but it demonstrates the point that the blue arrow at the bottom is return water coming back. The red is being drawn in from the thermal storage tank at a higher temperature than what's mixed going out, and the yellow is the mixed fuel or mixed energy that's going to the system to be delivered. So what you need in every case of thermal storage is you need a way to store the water from the boiler at a higher temperature than you're going to deliver it to the system. So that requires some mixing valve on the return and the delivery side of the system, or some way to blend or mix in water from thermal storage into an existing system. Thermally led CHP, when we say less than 2 cents a kilowatt hour, these systems are generally 95% overall thermally efficient. And basically what happens is you're taking higher pressure steam, you're dropping enthalpy from that steam, and it's turning that into work driving the turbine, and really what you lose or the inefficiency is generally in condensate. You can do superheated steam, but typically in our boilers and systems we start out with saturated steam. We run them through the system, come out the other end, and what happens is you've got maybe 3 to 5% condensate going through a 50% efficient turbine, and you usually get about, if you can deliver at less than 50 psi steam to the system, you can typically get about 8 kilowatts per 1,000 pounds of steam from a system with moderate pressures. And when I say moderate pressures, in the 250 psi range. Very old technology, mature technology, very reliable technology. We've had, I think on the projects we've done with 35 or so, 37 maybe installations, there are 5 to 7 back pressure steam systems. I have to go back and count again, but I think it's in that range. I think there may be 7 of them that have been installed, and owners are generally very pleased with the system. The other option is organic ranking system. An ORC is actually a little more thermal or electrically efficient. Overall thermal efficiency isn't any different. The challenge with organic ranking systems are the investment is higher typically, and so the quality of heat is also lower coming out of the system than it would normally be out of a back pressure steam system. And that's basically what drives your options, or the quality of heat you need to deliver to your system. It's a challenge to install an organic ranking system in that they require very high utilization year-round. On paper we can find lots of applications where they should work. In practicality, we have yet to install one because we have not found the correct parameters for thermal and electric use and sizing the systems. Again, absorption chillers, I gave you that example at a hospital. One thing that's not great about absorption chillers, unless there's some other benefit, for instance, unless you get a substantial savings on peak demand charges where you have very high electric charges, they generally don't pencil out. And the reason is that a single stage absorption chiller only has a coefficient performance of 0.7. So if I have to put in 1 million BTUs to get 700,000 BTUs of cooling, now that doesn't sound too bad unless you look at electric-driven system, and generally on systems the size that these are, in the 100 horsepower or 100 ton or bigger, the coefficient performance for these centrifugal systems is in the range of 5 to 1. So in other words, for 1 unit of electric I put in, I get 5 units of cooling out. So you can see then when you compare the absorption chillers to conventional centrifugal chillers, it's really a little bit tough to compete. You have to have really big advantages in energy costs to make them stand on their own. But there are cases and places where they do work and can be very effective. Again, this is an electrostatic precipitator. It was installed in a boiler room in Maine. Point out a problem with these. They actually have, and I don't know if you can see it, you can kind of see the light coming through behind this precipitator, and they brought in combustion air to the boiler and blew it across the electrostatic precipitator and got lots of condensation in that electrostatic precipitator, which is a big no-no. So that was not a good plan, but basically they can be fairly compact and fairly simple. They are a lot lower labor, and they're very reliable and very effective at emission controls, especially for finer particles. So if you're looking at institutional installation, the electrostatic precipitator is probably the way to go. If you've got a very industrial setup, then a baghouse probably makes a little more sense in that the economics are probably better. A multicyclone, usually they're in front of both an ESP and a fabric filter, although they don't have to be in front of an ESP. Multicyclones are typically the technology we would see for units under 10,000 BTUs an hour, or 10 million BTUs an hour of input. Where emission controls here for an electrostatic tongue twister. Electrostatic precipitator is in the range of, it's easy to reach 0.07 or 0.03 parts per million or pounds PM per million BTUs of input, which are the required standards for units up to 30 million BTUs an hour, and above 30 million BTUs an hour is 0.03. Multicyclones, typically we can tune them to get in the range of less than 0.2, 0.15, or 1.5 pounds to 2 pounds per million BTUs of input is typically the range they'll operate at. And fabric filters then can be just as effective as electrostatic precipitators. They tend to be a little more energy inefficient than electrostatic precipitators in that the pressure drop through the baghouse is usually greater than through the ESP. ESP takes some energy to run the electrostatic precipitators or the energize the plates, but it's not comparable to the amount of horsepower required for the pressure drop across a baghouse. So that was one-sided and very windy, so I'm going to take a little break or breather and let you ask questions about the systems and the design of the systems.
Does anybody have any questions? I'm going to unmute you so you can speak out if you'd like. Anybody have any questions? Well, they're not going to give you much of a break here, Tom.
I'm not sure they're awake. It's a long time to listen to a webinar. So. Okay. Projects. Again, I'm going to take you through some of the projects we've done and just show you examples of what the systems can look like, and they are, and just kind of talk you through some of these projects. This is Church Communities organization. This is a beautiful old monastery. It had a great library. It's got this beautiful chapel inside, and they use it as a high school for their community. It's the Bruderhof, I guess, is another name or term we use for the group. And this is their secondary education, where they bring students from New York, Pennsylvania. Generally, I think those are the two states that come from the communities they have there to go here and live here and attend high school. And so they rebuilt and remodeled this old oil boiler system, put in a Wiesmann 5.7 million BTU an hour, and I think the 2.3 million BTU an hour boilers in order to provide 100% of the heat from wood. They believe very much in renewable energy, and they use wood systems both in Europe and here. What was interesting about this project was that it, well, I guess we'll talk about it again a little later, sorry. But going back, what was interesting about this project, the whole system was designed as a steam system with steam distribution, and it was converted to hot water. And the amazing thing was, when you modeled the piping in the system, you literally had to put no controls on it in order to use the steam system for distribution for hot water. Every loop was balanced. It was pretty amazing. This was built in the early 1900s. I think it was completed in 1909. Some really, really talented engineers or HVAC folks laid this out. This is an art center in New Hampshire, northern New Hampshire. It was a fuel oil system. They did this project for under $100,000. It's got 290,000 BTU an hour boilers, pellet boilers, 300-gallon thermal storage. I think there was about 5,000 gallons a year of fuel oil, yes, 4,800. So there was about $10,000 a year in fuel savings on this system, and we were able to put storage in the basement of the system. These are the Okefin pellet boilers. They're pneumatically filled into the delivery tanks from these the 6-ton storage bag that's on the right. And all this was set in a very low basement, less than 7-foot ceiling at the bottom of that church. It's currently an art center. This is a Cordwood system. This is at Harvard Forest. It's Harvard's research forest that is about an hour and a half west of the University of Cambridge. Taken a little bit to get there, but as of a couple weeks ago, they were able to supply about 90% of their heating load from these 3 boilers to 5 buildings, I believe, are connected. Maximum capacity here is about 500,000 BTUs an hour for the 3 units. This, again, is a Bruderhof community in south central Pennsylvania. They installed this themselves, so the $600,000 price tag might be a little misleading, but they installed all the underground pipe. One of the lessons they learned here was closed cell foam insulation around pipe is not all created equal. When they say closed cell foam for buried insulated PEX pipe, you need to be sure that it's not closed cell foam wrapped in layers. It's got to be injected into the system so that it adheres both to the central pipe, the carrier pipe, and the outer coating and protection pipe. What happened, they put all their pipe in, purchased it from a reliable, reputable company, and they had some punctures in the pipe filled with water, and all the insulating value was gone, and they literally could follow the pipe all over campus. They ripped that out and put in a product that had an injected closed cell foam in the pipe, so there were no voids. If the outer casing of the pipe or outer protective casing of the insulation was damaged, there was nowhere for water to travel around the pipe. They pretty creative here. They hooked up a laundry. You can see the little picture in the lower right-hand corner with that little heat exchanger sitting on top of what looks like a furnace. They basically are preheating air going into their dining hall. They're also the next. They have thermal storage, and they also use wood heat and a heat exchanger to dry their clothes. It kind of derated their dryers, but not by enough that it matters, and tremendous savings, operating savings. Their fuel is free, either donated to them or collected on their property and processed through a chipper. Again, this is Espus. 85,000 gallons of fuel oil per year is offset. And again, a beautiful facility as far as overall design and quality. Was great. They could be repurposed. The monastery was going to have to be closed. It sits right on the Hudson River. You go up in that parapet and you can sit there and look up and down the Hudson. You can see the Vanderbilts and the Roosevelts facility or properties on the opposite side. It's just a beautiful location. They had their own dock in their heyday. They had their own wine cellars back in the 20s and 30s, and there's fruit orchards that are still operating there. It's a very unique facility and property. Crawford County, this is actually in my hometown. This is a 8.6 million BTU an hour boiler. This is unique in that it is steam to hot water in order to generate electricity. It was the goal of the school district that did this project to produce electricity, because that was this was in 2009 when they were doing this project, and electric prices were to be deregulated and increasing by up to 50%. And so they wanted some control of their electric. They're able to produce about 10% of their electric net to run their facilities with the combined heat and power project. It's also unique in there's 3 separate owners. There's a rec complex, a technical school, and then the high school that's owned by the school district. The tech school leased property to the high school on their property in order to build the unit. The school district went out and obtained the bonding to do the project. And then all three units go together on operating costs, and all three units split based on their historic fuel use. They split the mortgage or the capital cost, and they, based on metered heat delivered to the buildings, they split their operating costs based on current or future or whatever the current bill is, and the proportion is divided by the total amount delivered to each one of the units. So it takes chips, 300 cubic yards of storage, sends them into the steam boiler, comes out at 175 psi, goes through a 200 kW turbine generator, steam to hot water heat exchanger on the flip side, just a little shell and tube heat exchanger. They store 200-degree Fahrenheit water in a 6,000-gallon thermal storage tank. Then they have the 3 distribution pumps. Each one has its own separate flow meter and measures supply and return temperatures to each loop. So the individual loops are segregated inside the boiler room. So the piping brings the water from the buildings over to the facility, goes through a plate and frame heat exchanger in the facility, and is delivered back in and blended into their water. The high school has been able to offset almost 100% of their gas usage for space heating. The rec center is not quite as effective. A little bit of that is the issue and tuning of their different units and the way they operate, and the rec center, or the technical center, is able to offset about 75 to 80% of their heating load with the system. Sullivan County, New Hampshire is a steam system, steam distribution system, and they were able to hook up everything. 99.5% of the heating load on the facility was able to be connected to the system. And this diagram is not right. I'm not 100% sure if you can see this, but my pointer is going to this 140-foot line, steam line, and then from that 140-foot steam line, we go into a hot water system and pick up the last building on the facility. And so 100% of that facility is heated by the biomass plant. So it's about 125,000 gallons a year of fuel oil. It's offset, and about 10 to 12,000 gallons of propane. This is the VA hospital in Chillicothe, Ohio. It was the first VA hospital to go to wood heating, a biomass system. It's combined heat and power. There's a 350 kW turbine, about 1 million square feet, and they also, this is the installation where we put in the absorption chiller. They're generating 450 psi gauge steam in the system, 350 kW turbine. So their current price and distribution, everything for natural gas, is in the $7 range, and they still have substantial savings. When we did this project, natural gas obviously was higher, but they are still considerably better off running the biomass system than they are natural gas. Again, their net cost, distributed cost for natural gas last year was right at $7 a decatherm. In Gunderson Lutheran, this project was driven by 2 or 3 different reasons. One is they want to be 100% renewable, and this gave them the last piece to get them to like 95% of that. I think it's about 30% of their overall, and I think this is over all their systems. Jeff Rich could tell us for sure, but I believe they're looking at the total hospital system when they say they're in the 90-some% range using renewable energy, and they've done that in many different ways. And some of it is done with some offsets purchased, but most of it is by doing biomass, the biomass project, some solar PV and some solar thermal, also some anaerobic digester gas recovery from a brewery. So they have several different ways they've done it. Pleasant View Gardens, you can see this big thermal storage tank here. Nobody knows better about thermal storage than greenhouses, and the reason is that you could have a day like today here in Crawford County that the sun is shining and it's 30 degrees and you need to ventilate your greenhouses. The sun goes behind a cloud and all of a sudden you're going to have a huge demand. So this is a huge 100,000 gallon thermal storage tank, a 400 horsepower Hurst boiler is setting in this area. And you can see this is a little unique. They built this additional fuel storage in the lower right-hand corner of the picture. It's a hoop barn, and they bring and drop local tree trimmings and cuttings in. Then they have this big open corner to their boiler room and fuel storage or fuel delivery portion. In the lower left-hand corner, you're looking at the fuel rakes you can dump directly onto there from a bucket loader, or they can drive trucks directly on those rakes and unload them. So this is one place that did take advantage of some low-cost storage because they've got seasonally available product that they can get at a very low cost. They have sorting to accommodate the tree trimmings and other things that come in there. This is in New Hampshire. So the holy grail of biomass to electric is biogas to IC engines. Problem is that the difference between the gap between holy grail and commercially viable systems is pretty wide. So they've been working on this for a long time. Lots of companies claim to have it, but go try to buy one. And I'm able to get prices and quotes from 3 companies for systems in the U.S. One of them, they publish prices on the website, but try to get somebody to call you back, or I'm not sure they're really in business. There are 2 companies that are very viable and in business that are doing this. It's Borealis and All Power Labs. They make small systems, 45 kilowatts. Electric, 18 kilowatts electric. They're downdraft gasifiers, and if you're going to do utility scale projects, that's adding up a lot of those 45 kilowatt electric units, which is probably not going to happen very often. The units are all downdraft gasifiers, and the reason that downdraft gasifiers are what's used is that it tends to produce the cleanest gas, has the fewest tars in it. Approximate efficiency for electric on the high heat value basis is somewhere around 20 to 25%, and about 45% thermal, which, you know, compare that to back pressure steam, which you can only get 8% electric out. 6 to 8% is substantially more. Overall efficiency is worse or less than back pressure steam in that, well, I guess it's probably similar. If you look at the total combustion, it's not much different. So everybody has one, but you know, my favorite phone call was to Community Power, and we had a project that really this was going to fit for, and we thought this was viable technology. They claimed it was. They had lots of them advertised, and I asked for a price. We were doing a feasibility study, and they said, "How much money do you have?" And I scratched my head, and I said, "What?" And they said, "Well, you know, we kind of price them based on how much money you have." I'm thinking, yeah. We've followed them around a little bit. There is one unit that I know works very well, and it does it on walnut hulls, and it's in California on a walnut farm, nut farm. Walnuts are probably the perfect fuel in that if you look at the sizing of the walnut hulls are the perfect fuel. If you look at the size of the, it's got enough size and structure. They're very dry, but on almost everything else, they have a real tar problem and issue. There is a commercial unit in Europe sold by Babcock & Wilcox. They've installed several of them, up to 6 megawatts. They won't sell them in the U.S., and the reason they won't is that they claim there's not enough market here for them to set up and operate. The capital costs and the operating costs are high enough that prices for electric in the U.S. are just not justify them selling them here. So they haven't set up an infrastructure to do it. They use liquid gas cleaning, which is a little different. It's very effective. They're very reliable. They've been around for 15 years or longer. And again, the major engineering issue to overcome from biogas to IC engine is removing tars from the gas to make the modern IC engines operate efficiently. I guess if you had an older engine that didn't worry too much about how clean the gas was, and certainly did not have a blower on it for the air, you probably could make you work in almost anything. The problem is going to be the emissions and getting it permitted. So just to wrap up, a summary of the design portion of this presentation. Project design, you got to remember what the goal is, and usually that goal is trying to reduce costs while doing something environmentally friendly and sustainable. You got to choose the right system to fit. You got to know what you can connect with the system and can't connect with the system. Be realistic in what you're trying to do and what the actual economics are. Thermal storage is a key component in hydronic systems, and steam systems is a little tougher to make them make sense. You got to match the system with the resources that are there on both ends. And you have to really consider what the owner expects out of a system. How automated does this need to be? And that'll drive both your capital costs of the system and also drive what type of systems you can really look at or use. And wood energy is very clean. It's very efficient and very automated when it's done right. And I think that's what this whole project is about. Lou's program is to do it right. Scott, you want to take over?
Sure. Do we have any questions? I'm going to unmute everybody, and if anybody has any questions. Nope. Okay. Well, with that, next week we'll be looking at some more case studies of large fuel systems. Tim Bay, who's a business development guy, is going to look at that. Lou, one thing I had a question on is the modeling you guys do on projects. What kind of modeling program do you use? You use something like Energy Plus, or do you have another?
Wilson Engineering Plus.
Yeah.
Oh, okay. So you got your own.
Right.
Yeah, we just developed spreadsheets, Excel spreadsheets to do the work. It's pretty basic, simple.
Yep. Okay. I'm just curious. So do you use like a TMY weather data for that, or you're just kind of looking at?
We try to find weather data from the closest geographic place.
Okay.
Facility is, and then we input that in. And most of the institutional, we readjust the heating degree days to a base of 50 degrees because almost every institution, when it's 50 degrees out, is not going to be requiring heat because of internal heat load.
Okay.
Gain. So kind of readjust everything based on that scale. Depends on what the actual use is or what they do. The best projects are processes. They usually are constant loads and they're easy to figure out. And we love process loads.
Okay. Well, since we didn't have any questions, I guess we'll call it a day. If anybody has any questions, they can contact myself or Lou or Tom, and we'll try to get those answered. So with that, we'll call the session closed.
Okay, thank you, Scott.
Thanks, Scott.
Yep.